PV system converts electromagnetic energy emitted by the sun into electricity. It uses modules consisted of semiconducting materials that when exposed by solar radiation causes electrons to move, hence creating electricity current. This is known as the photovoltaic effect. Electricity generated by the PV modules is called DC. PV system depends on the availability of solar radiation and its total output is proportional to solar radiation. In the current energy transition, PV system has commonly used to generate electricity because solar is free energy resources. Solar radiation is locally available on almost everywhere in the world. The system has relatively low operation and maintenance cost, and solar energy is a form of green energy with zero emission. Extraterrestrial solar radiation, or known as solar constant, is equal to approximately 1003 watts per meter square. When reached Earth's surface, solar radiation received is only 1000 watts per meter square due to dust and other molecules absorption, reflection to space, and vaporization. It is also known as solar irradiance. Different locations on Earth might receive different solar irradiance. Thus, it is important to understand the basic concept of solar irradiance before we discuss PV system in more detail. We can distinguish solar irradiance into three types. Direct normal irradiance, or DNI, is the amount of solar radiation received per unit area that is always perpendicular to its incoming solar radiation. Thus, if PV module is tilted, then we must take into account the tilt angle when calculating DNI. Diffuse horizontal irradiance, or DHI, is the amount of solar radiation received per unit area that doesn't arrive directly from the sun, as it has been scattered by clouds and other particles. Reflected radiation is a portion of solar radiation that has been reflected by Earth's surface and received on a surface. For PV system application, we should also know global horizontal irradiance, or GHI. It is the total amount of solar radiation that is received on a surface. It is the sum of DNI, DHI, and reflected radiation if the panel is a bifacial. While it is possible to directly use the power generated by the PV system, in most cases we will need other power electronic devices to optimize it. SCC, PV and battery inverter, and energy storage are among the most important power electronic devices that accompany PV modules to create a PV system. The DC current generated from PV modules will enter power conditioning units to be modified into a conditioned DC power or converted to AC power, which is generally used by most of us. There are two types of PV systems that are widely used. On-grid system is a type of PV system that is connected to the utility grid. The frequency and magnitude of current that can be injected into this system grid is dictated by the utility grid. Off-grid system is a type of PV system that is independently operates without being connected to the utility grid. Thus, this type of system dictates its own frequency and magnitude. Throughout the video series, emphasis will be put on off-grid system. An off-grid system must be able to operate without the availability of utility grid. In other words, this type of PV system creates its own grid, and given the size of the power system, it is usually considered as a mini-grid. The term PV mini-grid will be used in the rest of the video series. As a PV module output depends on solar radiation, PV system output is intermittent. In other words, its output is not guaranteed to be constant for 24 hours. For a PV system to be able to serve 24 hours as a mini-grid, it needs to be equipped by energy storage. This storage, usually a battery system, will store the generated energy during the day and distribute it during the night. A complete PV mini-grid usually consists of PV module, power condition units that are SCC or PV inverter and battery inverter, coupled with battery system. In addition, it is also possible to combine it with other types of power plant, such as diesel generator, to form a hybrid PV battery diesel system. The picture shows some more detailed components that are commonly used in PV mini-grid system. PV modules array consists series and parallel connection of individual PV modules. This array converts solar radiation to electricity. Wiring is electrical installation of current-carrying conductor or cable connecting PV output to SCC or PV inverter. Combiner box combines PV strings or individual PV modules in parallel. It is equipped with protection devices. SCC or PV inverter modifies PV output voltage to the battery voltage level and controls battery charging. In case of PV inverter, its output can directly be used to inject current to the grid. DC distribution panel provides DC bus for DC connection. This panel connects SCC, battery bank, and inverter. Battery bank stores energy generated by PV during the day, so energy can still be used for which PV modules cannot generate it, such as during the night. Battery inverter converts DC bank battery voltage level into 230 volts AC. It is also used to protect the stored energy in the battery. Monitoring system is an instrument to monitor the performance of PV system. If telecommunication is available, the data can be sent remotely. Otherwise, it is locally stored in memory card. Powerhouse is a building constructed to protect most of the power electronic instruments, SCC, inverter, distribution panel, and battery. Lightning protection is used to attract and capture lightning strike, thus minimizing the risk of conductor receiving direct lightning strike. It is usually equipped with surge protection devices as well to avoid indirect lightning impact. Grounding system serves as a system to provide equipotential bonding busbar and put grounding system. Transformator is used to reduce losses when transferring power on a relatively long distance, about 1 to 3 kilometers. Distribution line and street lighting consists of posts that are combined with lighting system as the structure to connect cables from AC distribution panel to household. This can either be a single-phase system that is 220 volt AC or three-phase system that is 400 volts AC, depending on the size of the system. Household connection consists of MCBs and energy meters to limit current and energy usage respectively. PV system can be set up into two different configurations, DC coupling and AC coupling. In DC coupling, the main components of the system will be connected in DC bus, while in AC coupling, the main components of the system will be connected in AC bus. In DC coupling, PV modules will generate power. This power is used to charge battery via SCC. SCC acts as a DC-DC converter that will level the PV module's voltage to the battery voltage level. In addition, SCC uses MPPT algorithm to track the most optimum point with respect to the PV power curve for energy generation. PV inverter can directly inject current into the grid during sunny day. In AC coupling, battery inverter acts as a bidirectional inverter. When PV modules cannot meet the load demand, battery inverter will act as an inverter by discharging the battery to meet the load demand. When battery is not yet full during sunny day, battery inverter will regulate the battery charging process. Pros of DC coupling are higher efficiency during night application. If the battery inverter is turned off due to empty battery, PV modules can still be used to charge the battery and suitable for small size capacity. While its cons are smaller efficiency during day application and requires more components compared to AC coupling, and the PV system's capacity need to be extended. For AC coupling, the pros are relatively easier to be extended and requires less additional components, cheaper for bigger installed capacity, and higher efficiency during day application. While its cons are Smaller efficiency during night application, and should the battery empty, the grid will experience blackout and PV modules cannot be used to charge the battery. Technical feasibility study of PV system is as follows. Initial site identification, solar resource assessment with ground measurement and or satellite data, sun path analysis, shading analysis, demand forecasting, system design to determine required land area and system configuration, and simulation as performance analysis. In addition to the previous steps, in case of community-owned or operate PV mini-grid, the following feasibility studies must be performed. Identify ability and willingness to pay of the end users. Identify the income and occupation of the end users. And identify the potential group of people to manage and operate the PV mini-grid. Let us do a simple quiz. A PV mini-grid needs to be installed in a village that has a GTI equal to 5 kWh per meter square per day. The village consists of 150 households, and after performing a survey, it is known that each household consumes energy at maximum 900 watt-hours per meter per day. Assuming that the overall system efficiency is 80%, determine the minimum size of the PV array. The answer is as follows. Please continue to the next session by clicking the video thumbnail.